Alright, this is a second installment on sum and difference identities, and what we do with this set of identities is we're going to form new identities called double angle identities. What we do is we let A equal B in each case for the sum identities that we've already seen. So the sine of 2A, see a double angle, A and A, they're the same as each other, would be sine A cos A plus cos A sine A, because A and B are equivalent. These are equivalent terms. There are two of them, so I can write this as 2 sine A cos A. This is a double angle identity for sine. The sine of twice an angle is 2 times the sine of the single angle times the cos of the single angle. We're going to do the same thing for cosine now. I'm going to write cos of 2A because A equals B. It's now cos A minus sine A. Those are squares, so I can write cos squared A minus sine squared A equals the cos of 2A. Now, cosine double angle identity is a bit confusing because I can use the Pythagorean identities and substitute. When I see sine squared, I can say, oh, that's 1 minus cos squared. So then, cos 2A can also be written as cos squared A minus 1 minus cos squared A, or subtract negative is add, 2 cos squared A minus 1. Another identity. And hey, that was so much fun. Why would we stop there? Why not have cos squared theta be 1 minus sine squared theta, just using the Pythagorean identity in a different way, and go back to the start and substitute in, and we will get cos 2A equals 1 minus sine squared theta, oops, not theta, A, 1 minus sine squared of A, see the substitution, minus sine squared of A. So cos 2 theta then equals 1 minus 2 sine squared A. You may want to pause at this point and just ponder what I've done and reflect on that and look those over, because there's quite a lot of identities that are now appearing. Sine is relatively simple. There's only one way to write it for a double angle. Cosine has 3 different variants. Let's look at tangent. This is going to be tan A plus A, or tan 2A. Now it's tan A plus tan A over 1 minus tan A tan A. So tan of a double angle is 2 tan A plus tan A, 1 minus tan times tan is a squared, 1 minus tan squared A. So 5 more identities. And we do similar kinds of things with these as we did in the last lesson. So let's look at some examples. First up, solve a trig equation. Notice the double angle. Here's what I can do. I'll say, okay, well, another way to write the sine double angle is twice sine x cos x. Don't divide by cos x here. Cos x can equal 0. You'd be dividing by 0 potentially, which is undefined. Rather, gather to one side and factor. So there's cos on the other side, nothing left. Common factor, remainder, and this looks a lot like other trig equations that you've used now. I'm going to write cos x is 0, or sine x is 1/2 by using the 0 product rule. Something times something equals 0 leads to either of these being 0. This is quadrantal. The roots are going to be pi by 2 and 3 pi by 2 on the y-axis. This is a special angle with a reference angle. Alright, the reference angle is pi by 6, and I'm in quadrants 1 and 2. So in this case, x is pi by 6, or 5 pi by 6. Okay, at this point you should be getting the sense. By the way, this is the last lesson on trig identities, so there won't be more after this, but there are quite a lot of different manipulations and replacements that are possible in working equations and finding unknowns, aren't there? All right, here are some different expressions, and I would just like you to simplify them by recognizing how they're similar to the identities. Now, when you see sine times cos times sine or sine times cos are the same thing. We've got a 2 in front. This is the double angle identity for sine. So I will write sine, not 2 sine, it's just 1 sine. The 2 is part of the structure of the identity. Look back if you need to. Sine of twice the angle being 5 radians. So this is equivalent to sine 10. That would work for degrees too, by the way. 5 degrees becomes 10 degrees, 5 radians becomes 10 radians. All right, let's look at B. B is very similar to A. There's a sine times a cos. However, B is missing the 2. It is still a double angle identity, but I don't have the 2, so it must be half as large. So I'll write 1/2, because it's half of the value that we're used to seeing. Now the angle is pi by 14, and I double that. So this is half of sine pi by 7. Lastly, I see a common factor. I'm actually going to factor out -6, and you'll see why in a moment. 2 cos squared 5x minus 1. Now, when we see 2 cos squared minus 1, that's one of the forms of the cosine double angle identity. Let's look back and see. There we are. 2 cos squared of angle minus 1. So we're going to write this. We're going to write cos of twice the angle. The angle's 5x, so we're going to write the cos of 10x. Now, again, let's look back at the coefficient. We normally don't have a coefficient in front other than this 2. 2 cos squared minus 1 and a coefficient of 1. In this case, I have my 2 cos squared minus 1, so the bracket follows the structure that I need, but there's -6 in front, so the answer has to be -6 times that. You may want to pause and review that or make another problem up of your own at this point. They're a little tricky. All right, we've seen problems like these. This time I'm told cotangent in a quadrant and find tangent and sine. What I'd like you to do is pause. I'd like you to write theta in standard position. I'd like you to look at the identity for tangent of double angles and try to do a replacement and see how you do, then check back. Okay, here's my solution. Here's standard position angle. Move it up a little bit here. Cotangent is the x over the y, so x -3, y 4, okay, leading to a hypotenuse of 5. The double angle tangent identity is written right here. Here's tangent, and at this point all I have to do is simplify and do the math. So 24 over 7. All right. This next one has a little bit of a wrinkle in that this doesn't look like a double angle. This is twice a double angle. So your 2 theta behaves like theta. A little bit tricky. So this is going to be 2 sine 2 theta cos 2 theta. Now, sine 2 theta is a double angle identity. It's 2 sine theta cos theta. Don't forget that 2. And cos 2 theta is a double angle identity. I'm going to choose to write it as cos squared theta minus sine squared theta. There are 2 other ways to write it. All of them will work. Okay, at this point, we start doing some simplification. Sine of theta, that is 4/5. Cos of theta is -3/5. Then cos squared theta is -3/5 in brackets squared minus 4/5 in brackets squared. All right. Let's see. 4 times 4 times 3. 48 negative over 25. The bracket is 9 over 25 minus 16 over 25. All right. Negative 48 over 25 times -7 over 25, which is positive 4 times 7, 28, so 280 and 56. 336, 6, 25. There's our exact value. All right, just one more thing to show you quickly. There are actually three identities that occasionally come up. They're called the power reducing identities. We use the knowledge of cos 2 theta, written as 1 minus 2 sine squared theta, and isolate for the sine squared theta. And when we do that, the work is shown there. Sine squared theta can be written as 1 minus cos 2 theta over 2. It's power reducing. So you'll notice that there's an exponent of 2. It's squared. But it's equivalent to something with an exponent of 1, thus the reduction of the power. Likewise, cos 2 theta can be written in terms of cos squared theta, leading to a power reduction for cos squared. Also, tan squared is the quotient of sine squared divided cos squared. Using the information I just found, I obtain tan squared reduction based on cos. All of them based on cos. All right, that's it. Success with these identities and reviewing.